Hello everybody, Mr. Hasty here again. Today we're going to be talking about percent yield. So the word yield, we commonly don't use it this way in everyday language. Yield just means how much we make of something. So in our chemical equations we have our reactants and our products are what we yield. It's what we make. So our theoretical yield is how much we calculate we will make. So when we do all the math that we've been doing in 7.1 to 7.3, all the stoichiometry, we come up with, we're going to make 45 grams of this substance. That's our theoretical yield. The actual yield is how much we actually make. Now, the key here is that the theoretical yield is always kind of our high end. Unless we've messed up the math or severely messed up the measurements, our theoretical yield should always be higher than our actual yield. Depending on our level of accuracy and measurement, they could end up looking equal, but the theoretical yield is always higher than the actual yield. And we'll discuss reasons for that later. Now, the percent yield is just a percent of how much we got to how much we thought we were going to get. So the formula for percent yield, we're going to define it via the formula. The formula for percent yield is actual yield divided by theoretical yield times 100. So we just divide those two numbers and we multiply it by 100 to turn it into a percentage. So let's move on to our first example here. We are decomposing calcium carbonate into calcium oxide and carbon dioxide. So we actually did this in the lab. We would heat the calcium carbonate in a big test tube, and it turned from bluish to blackish. That was the calcium oxide. And then the carbon dioxide we actually captured in a gas tray and everything like that. So we're going to start with 350.0 grams of calcium carbonate, and we're going to determine the following. Part A, what is the theoretical yield of calcium oxide? How much calcium oxide are we planning on making? And then number two, if we actually produce 175.0 grams of calcium oxide, what is our percent yield? So whenever working with something like this, we need a balanced chemical equation. So we're starting with calcium carbonate. We have to remember how to make these things from our lessons on ionic compounds. Calcium is a +2. Carbonate's a polyatomic ion that's a -2. So that's a balanced ionic compound. And it's going to decompose. So we added some heat. We're not going to show that here, but basically decomposition means one thing turns into two. Turns into calcium oxide. Calcium's a +2. Oxygen is a -2, so we're good there. And carbon dioxide, which we know is CO2. Carbon dioxide, carbon 2 oxide. So what we want here is make sure this is balanced. We have one calcium on the left, one calcium on the right. We have one carbon on the left, one carbon on the right, and we have 3 oxygens and 1, 2, 3 oxygens. So we have a balanced chemical equation. So part A, we're going to determine the theoretical yield of calcium oxide. So we're starting with 350.0 grams of calcium carbonate. So the first thing you have to do is we're going to have to go all the way through the stoichiometric process. We're going to have to go from grams of calcium carbonate to moles, from moles of calcium carbonate to moles of calcium oxide, and then from moles of calcium oxide to grams of calcium oxide. So we're going to figure out how much is 1 mole, what's the mass of 1 mole of calcium carbonate. Now to do that, we have to do the molar mass. We add up 1 calcium, 1 carbon, and 3 oxygen off our periodic table. And we get 100.086 grams. Now we have to go from moles of calcium carbonate to moles of what we are looking for, which is calcium oxide. So because there are ones as our coefficients, turns out that 1 mole of calcium carbonate is 1 mole of calcium oxide. And finally, we do not want moles of calcium oxide, we want grams of calcium oxide. So 1 mole calcium oxide, and again this is a molar mass, so I have to get on my periodic table and add up 1 calcium plus 1 oxygen, and we get 56.077 grams of calcium oxide. So we do that calculation and we get, with 4 sig figs, 196.1 grams of calcium oxide. Now from there, we're going to do part B. That's how much theoretically we should get of our calcium oxide. We're going to take that number and we're going to use it to figure out part B. What is our percent yield? So I'm going to clear this. So for part B, our formula for percent yield is actual yield divided by theoretical yield times 100. So according to this, we actually produced 175.0 grams of calcium oxide. But according to our calculations, we were supposed to produce 196.1 grams of calcium oxide. So we do the calculation and we get about 89.24% yield. And that's how we commonly refer to it, as percent yield. You could say percent yield of calcium oxide. All right, now we're going to move on to a second example. So the second example is a bit of a process. We're going to have 4 parts here. We're going to have some pretty hefty vocabulary too. Hydrofluoric acid reacts with the silicon dioxide in glass to produce hexafluorosilicic acid and water. We start with 40.0 grams of silicon dioxide and 40.0 grams of that HF would be hydrofluoric acid, yielding 45.8 grams of hexafluorosilicic acid. So the first thing we have to get is a balanced chemical equation. So we're saying that hydrofluoric acids start with hydrogen, and hydrogen is a +1. We're adding fluorine, which is -1, so that's hydrofluoric acid, plus silicon dioxide. Silicon dioxide is a covalent compound, so it'd be SiO2. O2 is dioxide. And we're going to yield, and this is the tricky one, hexafluorosilicic acid. So I would not expect you to know what this compound is off the top of your head. It ends up being H2SiF6 plus water, which we know to be H2O. Okay, we got to balance this monstrosity. So as we go to, we have 1 H on the left, but we actually have 1, 2, 3, 4 H's on the right. 2 in the acid on the right and 2 in the water. So we're going to need at least 4 hydrogen. But it's also problematic because we have 1 fluorine on the left and we have 6 fluorine on the right. So I'm actually going to start there. I'm going to say that I have 6 hydrofluoric acid. So I have 6 hydrofluoric acid, and that gives me 6 hydrogens. We'll deal with hydrogen at the end because there's so many of them it can be tricky to deal with. We have 1 silicon on the left and 1 silicon on the right. We have 2 oxygen on the left, but we only have 1 oxygen on the right, so I need to double my water. So currently we have the fluorine balanced, we have the silicon balanced, and we have the oxygen balanced. So let's check on our hydrogen. On the left we have 6 hydrogen. On the right we have 2 hydrogen, and 2 times 2 would be 4, so we actually have 6 on the left and 6 on the right. This is a balanced chemical equation. So the first thing we're going to figure out is what is the limiting reactant. So this is from last section. To figure out what the limiting reactant is, we convert both of the masses given for our reactants, which are hydrofluoric acid and silicon dioxide, into moles and then compare their mole ratio. So we have 40.0 grams of silicon dioxide, and we're going to convert that to moles. Again, we add up 1 silicon and 2 oxygen off our periodic table here. And we get 60.084 grams of silicon dioxide. When we do this calculation, we get 0.666 moles of silicon dioxide. We're going to go through the same process for the 40 grams of hydrofluoric acid. So 1 mole of hydrofluoric acid is going to be adding up 1 hydrogen and 1 fluorine, getting us 20.006 grams of hydrofluoric acid. When we do this calculation, it should come out pretty close to 2. And with 3 sig figs, it does come out to 2. Now we have to compare that to the actual molar ratio in the problem. In the problem, we have 1 silicon dioxide to 6 hydrofluoric acid. So we need 6 times as many moles of hydrofluoric acid as we do silicon dioxide. So if we take 0.666 times 6, that means we would need 3.996 moles of hydrofluoric acid. And we don't have that. We don't have enough hydrofluoric acid to use up all of that silicon dioxide. So our limiting reactant is actually the 2 moles of hydrofluoric acid. So we're going to use that to do parts B and C. Just going to clear that out. So for part B, we're trying to find the mass of the excess reactant. That's the extra silicon dioxide we're going to have lying around. So we don't need to convert from 40 grams of hydrofluoric acid to moles. We already did that. We found out that we have 2.00 moles of hydrofluoric acid to start with. And we're going to continue on our stoichiometric process for the silicon dioxide. So we need to go from moles of hydrofluoric acid to moles of silicon dioxide. So there's a ratio given by the coefficients in the balanced equation. 6 moles of hydrofluoric acid will react with 1 mole of silicon dioxide. Now, we don't want our answer to be in moles of silicon dioxide. We want it in grams of silicon dioxide. Now, we actually did this calculation a second ago, and we figured out that there are 60.084 grams of silicon dioxide in 1 mole. So we do this calculation and we get 20.028 grams of silicon dioxide. That's how much of the silicon dioxide we're actually going to use. but we started with 40 grams. So to calculate our excess, and rules for sig figs, when you do sig figs, I guess this should be 20.0 according to our rules. So we would get 20.0 grams of silicon dioxide left over. So when we do this process, all of our hydrofluoric acid would react, and half of our silicon dioxide would react, and the other half would be what we call excess. All right, now we're going to move on to part C. Let me clear this. All right, so for part C, what is the theoretical yield of hexafluorosilicic acid? Man, that is hard to say. So we know we're going to start with 2.00 moles of hydrofluoric acid because that was our limiting reactant. According to the coefficients, 6 moles of hydrofluoric acid are going to react with 1 mole, or sorry, not react with, are going to transform into 1 mole of that acid, H2SiF6. And we have to convert that to grams still. So 1 mole of H2SiF6. To get the molar mass, we'd have to add up 2 hydrogens, 1 silicon, and 6 fluorines. And we would get 144.09 grams of that material. So we do this whole calculation, and that will get us 48.0 grams of H2SiF6. So that was the theoretical yield. That's how much we calculated that we should get. But according to this problem, we actually only got 45.8 grams of it. So now we're going to calculate the percent yield as part D. Let me clear this. All right. So for part D, the formula for percent yield is actual yield divided by theoretical yield times 100. The actual yield according to the problem is 45.8 grams. And our theoretical yield that we just calculated was 48.0 grams. So we simply do that calculation. And with 3 sig figs, we get 95.4% yield of H2SiF6. So let's talk about a few final thoughts. So why are theoretical and actual yields different? Beyond the limitations of measurement tools or mathematical errors, oftentimes it is hard when you make something in a chemical process to actually recover all of it. So if you're making something like hydrogen peroxide naturally decomposes. So by the time you actually make it and then take it away, it's going to have decomposed a little already. Or in the process, for instance, if you're using sulfur and you're heating it, if you have any oxygen present, some of it might react with that oxygen that's present to make sulfur dioxide. And so you can't use it all for the other reaction that you were attempting to use. So the main problems are that it doesn't always react completely, like all of the substance won't react the way you think it will, or actually getting the substance once you've made it is difficult. So why is this important? This is important because in practical chemistry, the percent yield affects the cost of the materials. So if we have raw goods, right? Let's just use gold because it's an expensive example. And we're turning the gold into another thing, whatever that thing is, if we have a process that's 95% efficient, then 95% of the gold we buy to make that material actually turns into that material. Yay. But if our process is only 75% of efficient, we need to buy more gold to make the same thing. And this affects the costs of items that we buy. Classic examples of this are large manufactured goods. So one of them being fertilizer, right? The efficiency of the process used to make it affects the final cost of the product. All right, so that ends our chapter on stoichiometry, and we'll be looking at doing our test towards the end of this week. Hopefully, you guys are keeping up with the videos and prepared, and I'll see you next time.